Hello, everyone. My name is Christiane, and I'm going to talk to you about thermal injuries from MRI. So of all the MR safety issues, why the focus on thermal injuries? Well, in a 10-year study, the FDA received and analyzed around 1,500 adverse event reports for MR systems between the 1st of January 2008 and the 31st of December 2017. It turns out that thermal events were the most commonly reported serious injury, comprising of 59% of analyzed reports. Mechanical events, defined as slips, falls, crush injuries, broken bones, cuts, musculoskeletal injuries from lifting or movement of the device, comprised of 11%. Projectile events made up 9%. And acoustic events at 6% were also reported. This report also broke down the root cause of the thermal events that I've listed here, with MR coils making up more than half of the list, and ECG electrodes with 15%. I'm going to illustrate these types of thermal injuries in the next few slides, so I do need to warn you that the pictures you are about to see are not pretty. These types of thermal injuries do happen in MRI machines everywhere, internationally, nationally. The patient's touching the bore and/or coils. There is a specialized MR foam padding that should be used, not sheets or towels, to prevent patients from touching the walls of the scanner or the local coils. This may be difficult in very large patients, but it must be done. Patient clothing can also cause burns. Various sportswear and underwear are now sometimes impregnated with invisible silver metallic microfibers that are undetectable to the eye. This is just one more reason that everyone getting an MRI scan should be stripped down completely, including underwear, and provided a hospital-style gown prior to MR imaging. Tattoos may lead to skin burns. The first-degree burn associated with the dragon tattoo pictured above is a distinctly rare phenomenon. More and more people today have at least one tattoo, so the incidence of a severe reaction is extremely small. People with tattoos may be scanned, but it is important to warn each patient to be aware of any burning or discomfort during the scan. Burns from cables in the MR machine touching the patient can occur. Skin contact must be avoided by padding and positioning. The wires should not be allowed to cross the patient. They should be run down the center of the MR system out between the patient's legs, not alongside of the system close to the RF coil. If more than one wire is exiting, try to leave a little space between them to prevent capacitive coupling. Foreign conductive metallic objects should not be left on a patient. Scanning a patient who still has a non-MRI compatible EKG pad, pulse oximeter, or anything of that sort should be considered a never event. This is an egregious medical error. These situations typically occur in typically ill patients who are being rushed to the MRI, with a whole team of healthcare providers urging the tech to begin scanning immediately. It is also important that patients avoid skin-to-skin contact. The kissing burns pictured here are what can happen if this rule is not observed. Typical scenarios include crossing the legs or holding hands. Okay, so here are the concepts that we will need to go over in terms of thermal injury. The first is a type of measure of tissue heating known as the specific absorption rate, otherwise known as SAR. We will go over how to calculate SAR, what the two permitted methods are for measuring SAR, the FDA limits, and methods for reducing SAR. In terms of implant heating, we will go over thermal injury from RF waves and gradients. Then I will talk about implant safety measures and how different implants are tested for heating. Then I will end the talk by showing different types of burns and what causes them. So now I'm going to talk about how to estimate SAR. It is the measure of the amount of power deposited by a radio frequency field in a certain mass of tissue. The units for SAR are power per kilogram. SAR is proportional to the electrical conductivity of tissue. Tissue conductivity varies by a factor of 10 across the body, where the highest conductivity is in high water content materials such as blood and urine, and lowest is in tissues like bone, fat, and lung. Foreign metal objects in the body are frequently highly conductive and significant. Even dangerous heating levels around these may occur. SAR increases significantly with body size. In a 2D model, SAR is proportional to the square of the body cross-sectional area. Because A is equal to pi r squared, where r is the radius of our patient, our model predicts that SAR is proportional to the body radius to the power of 4. When the third dimension is considered, SAR actually proves to be more closely proportional to r to the power of 5. SAR tends to be more concentrated around the periphery where the radius is larger. SAR is proportional to the square of the RF frequency. Typically, the RF frequency is chosen to closely match the alarm war frequency, which in turn is directly proportional to the static main magnetic field of the main magnet. So although things being equal, SAR depends on the square of the main magnetic field and of B1. So the same pulse sequence for the same patient imaged at 1.5T would therefore generate 4 times the SAR if performed at 3T. SAR is proportional to the square of the RF flip angle. This follows from the fact that the flip angle is proportional to the mean amplitude of the RF pulse, B1. Since SAR is proportional to B1 squared, it is also proportional to the square of the flip angle. So for example, a 180-degree pulse would create 4 times the SAR as a 90-degree pulse. SAR is proportional to the duty cycle, which represents the percent time in a pulse sequence RF is being transmitted. A more intense sequence with lots of RF pulses applied in a short period of time will generate a high level of SAR. The National Electrical Manufacturer Association, or NEMA, has developed guidelines for measuring SAR, generated by equipment using phantoms, incorporated in their standard MS-8 2016. These procedures are used by manufacturers to calculate SAR for their MRI systems. There are 2 basic methods that are permitted. The first is the pulse energy method. This method is a little complicated. Basically, a directional coupler is used to measure forward and reflective power together with an oscilloscope to measure peak-to-peak voltages. Coil losses are assessed using a non-loading phantom, while a loading phantom is used to measure sample losses. The next one is calorimetric method, which is more straightforward, and as the name suggests, it uses an insulated loading phantom with direct measurement of temperature. From the degree of temperature increase, the absorbed energy and SAR can be computed. As a crude approximation, a SAR of 1 power or 1 watt per kilogram would increase the temperature of an insulated slab of tissue by about 1 degree Celsius per hour. SAR measurements are displayed on the scanner. The calculation of SAR in human subjects is very complicated and imprecise, and it requires sophisticated mathematical modeling and computer simulations to estimate it. All commercially available MR scanners have programs that estimate SAR values automatically when a specific imaging protocol is selected and warn the operator if regulatory limits are likely to be exceeded. However, each manufacturer uses a different proprietary algorithm, so the calculated SAR values may differ substantially among vendors. To get a reasonable estimate for SAR requires an accurate patient weight to be entered by the technologist. Having said that, most modern scanners monitor transmitted power to prevent excessive RF exposure in case an incorrect patient weight has been entered. The scanner will estimate energy deposition for tissue. It won't account for any metal in the patient, which is much more efficient at absorbing RF energy, but it does matter where the metal is located in the body. So an aneurysm clip deep within the body won't have the same impact as if it were on the surface. Another example is plates in the femur will heat up because the femur isn't as deep in the body. Metal on the surface that isn't ferromagnetic, like tattoos, orthodontic work, makeup, etc., can also cause heating. There is also heat dissipation that can occur in some applications. So for example, if you are imaging near the heart and there's an intravascular stent made of of supermetal that is not ferromagnetic, it may not heat up as fast because there is constant blood flow that helps to dissipate the heat. The IEC and FDA jointly worked to develop the first international standards for MR equipment safety, codified as IEC 606-01-233. This document classified SAR into various subtypes known in the table and established 3 modes of scanner operation based on the perceived risk to the subjects. These are normal mode, first level controlled mode, and second level controlled mode. Criteria for each operating mode are based principally around SAR, but also include factors such as static field strength, rates of time varying gradients, area of the body image, and temperature rise. The normal operating mode is the routine level at which most clinical MRI today is performed, being considered safe for all patients regardless of their condition. The first level controlled operating mode is defined as the one where certain imaging parameters may cause physiological stress, such as peripheral nerve stimulation or tissue heating. Active medical supervision is required to use this mode to ensure that a careful assessment of benefits versus risks have been assessed. The FDA requires equipment operating in this mode to display and record the SAR levels and display a warning that the first level mode is about to be reached. The MR scan operator must acknowledge this at the console before being allowed to proceed with the scan. The second level controlled operating mode is known as the research or experimental mode. This level is reached when an operation may produce significant risk to patients. Second level mode may only be used under an appropriate ethics or human studies protocol. Special security measures such as software password lock must be used to prevent unauthorized operation in this mode. In a previous slide, I talked about what SAR is proportional to. So things like tissue conductivity, patient body size, field strength, and RF flip angle, duty cycle. Considering these factors leads to a better understanding of what sequences produces the highest levels of SAR and can help provide a wide range of potential strategies for reducing it. Since SAR is proportional to the square of the flip angle, sequences with the highest SAR levels tend to be those containing a large number of 180-degree refocusing pulses applied over a short period of time. Fast spin echo is the archetype, followed by the inversion recovery family. Saturation pulses of all types, fat sat, spatial sat, and especially magnetization transfer may cause SAR limits to be exceeded. As a rule, gradient echo sequences produce much lower SAR effects as they use gradient reversals rather than refocusing pulses to rephase the MR signal. Exceptions to this rule are GRE sequences performed at extremely short TRs, such as BSS-FP Fiesta and TOF MR, the latter of which also include traveling saturation bands that add to the SAR load. If these sequences must be used, interleave them in the protocol with lower SAR sequences to allow tissue cooling in between. You also need to understand that by reducing SAR, there are consequences, as I will explain in the next slide. So I suggested using gradient echo sequences to reduce SAR. However, given our knowledge of MR imaging, that will increase susceptibility artifacts. I suggested reducing the flip angle, which is especially useful for super short TR sequences, like fully rewound GRE. However, this may affect imaging contrast and the signal-to-noise ratio. Increasing TR without increasing the number of slices and decreasing the number of slices without reducing TR will incur a time penalty. I didn't mention it, but SAR can be reduced by decreasing the number of case-based views. And decreasing the number of case-based views can be done by decreasing the number of phase encode steps, which will result in a loss of resolution, or using parallel imaging, which may result in SNR loss and artifacts. Specifically for fast spin echo, the SAR can be reduced by decreasing the echo train length, ETL, which will incur either a time or slice number penalty. or reduce the angle of refocusing pulses from 180 to 135 to 150, which may reduce the signal-to-noise ratio. You can also use a low SAR or variable rate selective excitation pulses, otherwise known as bursts, if they are available on the scanner. However, be aware that this will incur a time or slice number penalty. Okay, so we all know that energy deposited in tissues during MRI causes tissues to heat and result in thermal injuries. But how does MRI cause thermal injury? When you have a changing magnetic field, it can generate electric eddy currents in accordance with Faraday's law of induction. When these currents encounter electrical resistance, thermal energy is produced. The conductive material in which eddy currents are induced may be metallic components of the MR scanner, such as other coils, wires, or devices within or on the patient, and the patient as a whole. The degree of energy transfer is quantified by SAR. So, for example, when a metallic implant is present, energy may be deposited both within the implant itself as well as in the immediate adjacent tissues. What happens precisely depends on the shape and composition of the material and whether we are dealing with RF or switch gradient sources. So there are two ways to change the magnetic field. The first is RF heating produced by currents in nearby tissues caused by implant-related intensification or electric fields. Then there is gradient heating, which is due to eddy currents within the implant itself, with secondary heating of soft tissues. It can be intensified by scattered radiation on the surface of the implant. Just a reminder that the gradient field gives us the spatial localization of signal in MR imaging, and RF field gives us the grayscale voxel values. So both RF and gradient fields produce tissue heating, but the effects are different because of the geometry, magnitude, and frequency characteristics of each. In typical MRI applications, RF fields are designed to be relatively uniform over the entire volume of the transmit coil. They have maximum amplitudes on the order of 0.01 millitesla and frequencies in the 100,000 kilohertz range. Time-varying gradient fields for spatial encoding are designed to have amplitudes near zero at isocenter, increasing to the range of 10 millitesla near the ends of the scanner bore. Their base frequencies lie in the range of 1 to 2 kilohertz, with harmonics extending to over 10 kilohertz. This is a simulation of gradient coil versus radiofrequency heating in an adult with a unilateral hip prosthesis. In this case, gradient heating is confined to the immediate vicinity of the implant and greatest in the extended cross-section of the acetabular cup. RF heating can create hotspots throughout the body. RF heating near the implant is most prominent at pointed elements, that being the tip of the femoral stem and the screw in the acetabulum, in the superior acetabulum. RF-related heating is the dominant cause of heating around an implant. Those swirling eddy currents induced by the RF fields do not penetrate to the center of the metallic implant, but instead reside almost entirely along its surface. RF-induced currents flow through a tiny fraction of the total implant mass at its surface and do not cause direct heating to the implant. In the soft tissues immediately adjacent to the implant, however, electric fields and currents become concentrated and very high levels of heating can occur. One special example of localized RF heating around an implant is known as the antenna effect, seen in elongated implants like wires or electrode leads whose lengths are between 1/4 or 1/2 the RF wavelength. For MRI, wires measuring about 26 centimeters at 1.5 T or 13 centimeters at 3 T are the most likely to create heating problems. In this scenario, electric fields can become augmented at the tip of the device, leading to heating and the possibility of internal burns. Gradient-related heating is entirely different. The deposited energy within the implant itself indirectly heats surrounding tissues. Because gradient switching frequencies are 100,000 times lower than RF frequencies, induced electrical currents are not confined to the skin of the implant, but circulate throughout it. Heating may occur in implants with large cross-sections, having low resistance, closed current loops such as hip prosthesis, pulse generators, and infusion pumps. Gradients do not generate appreciable eddy currents in tissues, so any thermal effects are due to heat diffusion from the implant itself. Several international safety organizations and government agencies have published relevant standards and methods for estimating and measuring implant-related heating in the MR environment. The three most important are the International Electrotechnical Commission, IEC, the American Association of Testing and Materials International, ASTM, and the International Standards Organization, ISO. The IEC 60601-2-33 is a 100+ page document dealing with multiple aspects of MRI safety and performance, of which implant heating is only a small part. One of the important advances of this standard with regards to implants is the recommended use of B1 plus RMS over SAR, which we will go into in a later slide. The ASTM standard F2182 is restricted to RF heating of fully implanted passive devices into cylindrical magnets at 1.5T and 3T. I'll show an image of this method in a future slide. The ISO/TS is the most comprehensive approach to implant heating issues. A 4-tiered approach is taken, each level progressively resulting in less restrictive conditions for imaging for the implant, but requiring a more complex analysis. I'll go into each one briefly, starting with the IEC's method. In brief, the sinusoidal fluctuation of the transmit RF field, B1, the green arrow, can be decomposed into two components, each half as large. A component rotating in the same direction as the nuclear precession, B1+, and a component rotating in the opposite direction, B1-. The B1+ subfield is responsible for tipping the nuclear magnetization. The B1 subfield rotates opposite to the spin system, generating only heat via induced electrical currents, but having no effect on nuclei. The example below shows a linearly polarized B1 demonstrating equal and opposite B1+ and B1- components. In the modern era, nearly all transmitted RF coils are circularly polarized, meaning ideally that B1+ is equal to B1 and B1- is equal to 0. The image is showing decomposition of an oscillating RF field, B1 green and B1+ red and B1- blue subcomponents. The term B1 plus RMS refers to the root mean squared value of B1 plus averaged over a period of 10 seconds. B1 plus peak values may also be used. B1 plus RMS can be thought of as the supplemental metric to SAR for controlling RF powered deposition. Most modern scanners report this value along with SAR for each sequence, but scanners produced before 2013 will probably not. B1 plus RMS is a more precise exposure metric because it depends primarily on the scanner and sequence and less on the patient than SAR. The image is showing the definition of B1 plus RMS for a simple sine wave. Because the wave has equal positive and negative portions, the simple average B1 plus average is meaningless and always equals 0 over any complete cycle. By squaring the B1 plus amplitude at each point before summing over the time interval t, the root mean squared produces a positive value. For a sine wave, it can be shown by simple calculation that B1 plus RMS is equal to B1 plus peak times the square root of 2, or approximately 0.707 times B1 plus peak. The IEC describes a method by which manufacturers may calculate B1 plus using the principle that B1 plus scales linearly with voltage supplied to the transmitter. However, because each patient presents a different electronic load to the RF coil, the voltage required to attain a given flip angle must be empirically determined. This calibration occurs during pre-scan, where 1 millisecond rectangular pulses of different amplitude are tested until the reference transmitter voltage, Vref, to achieve a perfect 180-degree pulse is determined. Once Vref is known, the magnitude of the B1 plus field for any other transmitter voltages can be easily calculated. SAR is directly proportional to B1 plus squared. The advantage of using B1 plus RMS over SAR is that B1 plus RMS can be directly calculated by measuring transmitter voltages producing the incident RF irradiation. Because B1 plus RMS only depends on the flip angle, it is independent of B naught, the main magnetic field, unlike SAR, which is actually proportional to B naught squared, or the main magnetic field squared. It should be noted that actual B1 and B1 plus vary by location inside the subject and are determined as spatially average values within an axial center slab. The error in this estimation may be substantial, particularly if an implant is present. In fact, the major issue of B1 plus RMS metric is for the conditional labeling of implants. Implant manufacturers are responsible for determining the maximum B1 plus field compatible with safe use of their device in the MR environment. So this document is intended to provide general guidance on how to adjust MR scan protocols in accordance with the specific absorption rate, SAR, and B1 plus RMS limits identified in the MRI guidelines for Medtronic deep brain stimulation systems. The scan protocol adjustments described in this document should only be used by qualified MRI scanner operators. This document goes into how to configure the protocol, make adjustments to sequences, and verify the predicted B1 plus RMS value. This is an illustration of the ASTM standard. The image on the left shows a procedure is described using a saline-based gel-filled phantom of approximately the same dimensions of the body part where the implant is located. The gel is doped to have electrical and thermal properties similar to the human tissue. Temperature change in and around the implant is recorded following 15 minutes of continuous RF exposure to a SAR of at least 2 watts per kilogram averaged over the volume of the phantom. These images show a gel-filled torso phantom for evaluating heating of a pacemaker and wire shown in the arrows. A black temperature probe is attached to the tip of the pacemaker lead. On the right, a heat map is assessed by an infrared camera after RF excitation shows a temperature increase at the lead tip. Lastly, I'll briefly explain the ISO TS standard. In brief, the 4 tiers are as follows. 1. RF heating measurements made in phantoms for worst-case scenarios where no modeling is required. 2. Basic human body electromagnetic modeling to predict locations of the highest electric field to which the implant might be exposed. In general, Tier 1 and 2 assessments are usually done for small, compact devices such as cochlear implants, pressure sensors, implanted monitors, and leadless pacemakers. 3. Modeling of both the human body and the implant with calculation of electrical fields tangential to the device. And 4. Concurrent human and implant modeling. Tier 3 is required for larger and more complex devices, while Tier 4 is only infrequently performed due to its complexity. All mathematical simulations must be verified by actual measurements in a tissue mimicking phantom similar to that pictured in my last slide. In addition to RF heating, ISO/TS 10974 describes similar tiered procedures for evaluating gradient-induced implant heating. Methods for measuring gradient-induced vibration of implants are also included. Here are two important FDA posters to keep in mind. The first one talks about MRI burn prevention, and the other one talks about labeling, which is very important. So please go check those out on the websites. I would like to thank you for listening to my talk.